All right, hey everybody. We're going to look at kind of our final application of first derivatives and derivatives in general. That is optimization problems. So these are all going to be kind of word problems where we have some value we're trying to either maximize or minimize subject to certain constraints. So for a problem like this, you're going to want to until you become really familiar with them, you should probably follow these steps to solve it. So first, you really want to read it very clearly and understand what's going on in it, right? Understand what's known, what's unknown, what is the variable, things like that. Draw a diagram if you can. It's often going to be really useful to do that. And then to introduce some notation to label the different parts that are kind of variable and so notation that's going to be useful for kind of abstracting this into some mathematical function. And so the function, so especially the value that you're trying to optimize, either maximize or minimize, you want that to be a function. If it's a function of multiple variables, you're going to want to figure out a way to simplify it so that you can use substitutions so that in the end it's a function of just one variable. And then you want to figure out what is the kind of the range of possible values for that variable and look for the absolute maximum or minimum value of the function on that interval to solve the problem. So let's take a look at an example. So a farmer's got 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. So what are the dimensions of the field that has the largest area? So here, I'm going to draw this little river. Okay, so he's making a rectangular fence that has these dimensions. Have a width of x and a height of y, let's say. And what we have is that the farmer has 2,400 feet of fencing. So the total fencing is going to be x plus, well, there's x up here, x plus y, right? So this is going to be 2x plus a y. And what we are interested in is the area. The area is x times y, right? This is what we're trying to optimize. We're trying to optimize the area, maximize that, subject to the constraint. Now the constraint's going to actually be the substitution that we're going to use. Notice I can write this as, since 2,400 is 2x plus y, I can write y is equal to 2,400 minus 2x. And that's exactly what I'm going to do. I'm going to plug that in place of y. So actually I'm going to have x times 2,400 minus 2x, which is 2,400 x minus, we get 2,400 x minus 2x squared. So what we're going to want to do is take the derivative of this function, the derivative of 2,400x minus 2x squared, that's going to be 2,400 minus 4x. Setting this equal to 0, so we're going to get 4x is equal to 2,400. In other words, x is going to be 2,400 divided by 4, that's 600 feet long. And if x is 600, that means y is going to be 1,200. And so that's going to be the dimensions, that's in feet, the dimensions of the largest area fence that can be enclosed. So if a cylindrical can is made to hold 1 liter of oil, we want to find the dimensions that will minimize the cost of the metal to manufacture the can. So we want to minimize the surface area of this thing. So cylinder, let's draw a little cylinder, and we'll label bits of this thing. We know that the dimensions are going to be the radius of this thing and the height of this thing, right? We know that the surface area, call it S, is going to be the circumference of the amount. If you unroll this thing, these are this is kind of like the unrolled metal, right? So this thing is H, and then the total we have 2 pi r. That's the the total like length of this. That's the circumference of this circle, and these are both pi r squared. So the surface area is 2 pi r plus pi r squared. Plus 2 pi r squared. It's 2 pi r times h. Now, we're told that this holds 1 liter of oil. And so the volume, that's 1 liter, is equal to the height times pi r squared. That's the area of the radius times the height. That's the volume of this. Okay, so the volume in liters. But because we're going to be measuring this in units of length, the radius and the height, we want to remember that one liter is 1,000 cubic centimeters. So actually, we're going to convert this. This is one liter. We're going to change it to 1,000 cubic centimeters. Is h times pi r squared. So we're converting the units to centimeters now, and that's going to allow us to calculate this thing. So the surface is, I'm going to make a substitution. Let's clean this up. So the height, I'm going to eliminate h. That's going to be 1,000 over pi r squared. So by plugging that in, the surface area is now, it's just a function of r. It's 2 pi r times 1,000 over pi r squared plus 2 pi r squared. You can see that the pi's will cancel here, and actually there's an r down below which is cancel with that. So we have 2 times 1,000, that's actually 2,000. That's 2,000 over r plus 2 pi r squared. Let's find the derivative of the surface area. That's going to be negative 2,000 over r squared plus 4 pi r. To get common denominators to find out when this thing equals 0, I'm going to multiply this by r squared over r squared. And what I'm going to get then is 4 pi r cubed minus 2,000 is over r squared. Okay, if I set that equal to 0, that's going to be 0 only when the numerator is 0, right? When 4 pi r cubed minus 2,000 equals 0. Otherwise known as when r cubed is equal to 500 over pi. So that means r, the radius, is going to be the cubic root, right, of 500 over pi. Now, since r is known to us, and actually this I'm gonna approximate this in decimals. That's about 5.42 centimeters. The height is going to be 1,000 divided by pi times 5.42 squared, which comes out to be about 10.84 centimeters. So that gives us the optimal radius and the optimal height of the can that's going to hold 1 liter of oil. That's going to optimal in terms of minimizing the surface area. Interestingly enough, you notice that this thing is twice as tall as it is wide. Notice that? All right. Oh, actually, the radius. No, that's just as wide as it is tall, because the radius, that's only the diameter is going to be r twice r. Yeah, this thing ends up being twice as just as wide as it is tall. Yeah. Okay, so this is a test that we can use to figure out whether a critical number of a continuous function, if we found an absolute maximum value or a minimum value. And really it's a matter of looking at if you're looking at the sign of the first derivative, if it's positive and then it's negative, that means you have a local, or sorry, I should say this is the this is the then we have a maximum in that case. And if the first derivative graph looks like this, that where it's negative and then it's positive, that means that you have found the minimum. But this is pretty similar to what we were looking at before with the signs of graphs, so I don't think this is anything that's that new. Okay, let's look at trying to minimize this distance. We want to find a point on a parabola y squared equals 2x that's closest to the point 1, 4. So the parabola is going to look roughly like this. If we were to graph this out, it's going to be kind of a squatted down parabola. And if you plug 1 in for x, you would get 2 in for y. So the point 1, 4 is over here. So if we were to try to like estimate this, we would say, well, probably this is probably around where this point might be. Now, how do we even do this? Well, the distance between some point for some point xy to the point 1, 4 is the square root of the difference in x's, so it's x minus 1 squared plus y minus 4 squared. So we're trying to minimize this distance. I'll call this d. Now, we actually don't. One thing that is true about distance is that it's a monotonic function, which means that which is I say, like the distance squared is going to be minimized at the exact same point when the distance is minimized. So actually, it's going to save us some headache to try to look at the minimum distance, and I might as well just call this f. So the distance squared is x minus 1 squared plus y minus 4 squared. Then I just dropped the square root. I'm going to focus on minimizing this function of x and y. But I can't, I don't want to just look at a function of x and y. I want to use a substitution, and for this, it's going to be easiest to substitute out the x, because this substitution gives me x is 1/2 y squared, and I'm going to plug that in here. So d squared, let's call this now f of y is 1/2 y squared, or I guess I could write y squared over 2 minus 1 squared plus y minus 4 squared. And I want to find the minimum of that. Well, okay, let's do it. The first derivative is going to be 2 times y squared over 2 minus 1 times the derivative of y squared over 2 plus 1, which is going to be a y, because it'll be 2y over 2, that's a y, plus 2 times y minus 4. And I'm going to clean this up a little bit. This is going to be, distribute the 2, and we're going to get y squared minus 2 times y plus 2y minus 8. So this is actually y to the third minus 2y plus 2y. It's going to be, the 2y's are going to be canceled, and so I'm going to have y to the third minus 8. That's the first derivative. So if I set y to the third minus 8 equal to 0, y to the third equals 8 has one and only one solution. Y is equal to 2. And when y is 2, x is going to be what? That's going to be 4 equals 2x. That means x is going to be 2. So it wasn't too far off from what I kind of imagined it was going to be. the closest point is the point 2, 2. That's the point on the parabola that's closest to the coordinate 1, 4. All right, cool. Okay, so a man launches his boat from point A on the bank of a straight river, 3 kilometers wide, and wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. He can row 6 kilometers an hour, and he can run 8 kilometers an hour along the bank. Where should he land the boat to get to point B as quickly as possible? Let's look at this in terms of a little graph. So he's starting here on, and if he wanted to go straight across, that would be 3 kilometers, right? And he wants to get to point B, and this distance here is 8 kilometers down. So the point of this is he can row straight across either to this point here, or he can row to some point. Let's say he can row like X units. If he rows X units down, then he can run the rest of the way. So we want to find out how long it takes him to row along the diagonal and then to run down the rest of the way. So he's going to row. Well, let's find out what the hypotenuse is. So this is going to be the square root of so the base squared, which is x squared, plus 3 squared, which is 9. So he's going to row for square root of of x squared plus 9 kilometers at 6 kilometers per hour. And he's going to run for, what's the remaining distance? It would be 8 minus x kilometers at 8 kilometers per hour. So we'll find the total time, I'll call it t. The total time it takes is going to be, so if you want to find the amount of time it takes, you would have to take the kilometers and divide it by your speed. That's going to tell you how long it takes to get there, right? If you're going 60 miles an hour and you want to travel 30 miles, 30 divided by 60 gives you 1/2 hour. So it's going to be square root of x squared plus 9 over 6 plus 8 minus x over 8. That's the total amount of time it's going to take for this fellow to reach his destination. So we take the derivative, and then we're going to try to figure this thing out. The derivative is going to be, let's see, we have the 1/6. This is going to be 12 square root of x squared plus 9. And then up top, it's going to be the derivative of x squared plus 9, which is going to be 2x. And then over here, the derivative of 8 minus, this is 8 minus 1/8 x. So that's going to be actually negative 1/8. So if I set this thing equal to 0, well, let's do a little. I can at least cancel that a little bit, clean it up. Set it equal to 0. Set which is the same as saying x. Let x over 6 square root of x squared plus 9 equal 1/8. I'm going to multiply both sides of these things. Let's see. I'm going to multiply by 8 on both sides, and I'm going to multiply by this denominator on both sides. So I'm going to have 8x equals 6 square root of x squared plus 9. And I can solve this thing by, I'm going to square both sides of this thing. So I'm going to get 64x squared is equal to 36 x squared plus 9. And so we can, this is 36 x squared plus 324. Okay, so let's get the x's to the other side. So it's 64 minus 36. 28x squared is equal to 324. 324 divided by 28. So let's put it this way. X is going to be the square root of 324 over 28. Okay. Which is roughly 3.4 kilometers. So that he wants to row to 3.4 kilometers down the bank, and then he's going to get out and he's going to run the rest of the way. All right, now let's find the area of the largest rectangle that can be inscribed inside a semicircle of radius r. Well, we'll just draw this semicircle of radius r, and we're going to try to figure this out. Okay, so let's have that be r, and inscribing a rectangle means you just take some point along this, and we're going to make a rectangle that fits it. So if this point here is the point xy, then the area is going to be it's 2x by y. So it's going to be 2xy. We want to maximize 2xy. Now, we do have a restriction on y, or relationship between the two. Because we're inscribing this thing in a rectangle, this point is on the curve. This circle is r squared equals x squared plus y squared. That's the full circle. The semicircle is r equals positive square root of, actually, let me, I'm going to solve it for y squared. Y squared is r squared minus x squared. So if I take a square root, I'm going to get the function that gives me just the top half of the circle, the semicircle in the first and second quadrants, r squared minus x squared. So I can actually write a is, or I can write it if you like, a of x, the area when I'm at x, is 2x times the square root of r squared minus x squared. So let's find the first derivative using the product rule, or let's distribute it. Let's put the x inside. Let's write this as 2 times the square root of r squared x squared minus x to the fourth. So this is going to be, if I take the derivative of this thing, it's going to be, I'm going to have 2 times, and then down here I'm going to have 2 square root of r squared x squared minus x to the fourth. And up top I'm going to get the derivative of r squared times x squared minus x to the fourth. So that's going to be 2 r squared x minus 4x to the third. And now remember, the first derivative is only 0 when the numerator is 0. And so I don't really care about the denominator. So let's just write 2r squared x minus 4x to the third equals 0, and solve this thing. I'm going to factor out a 2x, get r squared minus 2x squared equals 0. And looks like this is going to be 0 when x is 0, or when this thing is 0, when r squared is equal to 2x squared, when x squared is equal to r squared over 2. In other words, when x is equal to the square root of r squared over 2. That's r over square root 2. In fact, if you think about it, what's happening there, if this is r, if you were to go up at a 45-degree angle, this point here would be r over root 2 comma r over root 2. You'd be making a square in this quadrant and a square in that quadrant as well. So there you go. That's going to be but if we're trying to find the area of the largest rectangle, it's going to be 2 times x times y. Well, y is equal to x, it turns out, and because you could plug this in to this relationship here, and you'd get that. So the area at r over root 2 is going to be 2 times r squared over 2. That's just r squared. That's the largest rectangle that can fit into this. Okay, I think we're going to stop there. So optimization problems, a lot of derivatives, finding maximums and minimums. All right, bye.